Okay, a few words about the final exam. So as you know that assignments and quizzes should be your main source of study and preparation, especially starting from the most recent ones and going backwards. And you can guess that there'll probably be a gravity question from assignment 13 and a torque, rotational inertia, rotational kinematics question from assignments 10, 11, and 12. And then before that you have momentum and energy. And most of the questions will be from the assignment and quiz type questions, but there will be essay questions, and I'll talk about that later. In addition to that, you have the equation sheet, and so let's scroll through the equation sheet and take a look at what's there. So on the first page you see some information that we discussed recently about formatting. So there are some, depending on how we number them, 6 to 8 different steps that you take when you're doing problem solving. And this outlines that for you and how grading of those problems is done. And then you have 2 pages of equations. And this summarizes all that we've learned all semester by section in chronological order. So you should really step through all these equations. Make sure you understand all the symbols. Make sure you know how to put equations to words if you're answering an essay question. Like, look at this equation. What is this? This is the definition of what? Displacement. The change, and the way you put it in words is the change in position is the final position minus the initial position. These are the equations you would use if you had a question distinguish between average and instantaneous velocity, right? So we do have then our kinematics equations, our equations for vectors. Then we did forces. Those are all our force equations, work and energy. The definition of work is an integral involving a dot product, which is the product of 2 vectors times the cosine of the angle between them. Can you discuss this? And then our conservation of energy equation, right? Do you know how to talk about that? The energy of a closed system is constant. Work is the way in which energy is added or subtracted from a system. And the MOP questions, which are in the assignments, right? There will be MOP questions, uses an alternate version of this. That's one of the questions. We'll go over that. Then we spent a week on impulse. Impulse is an integral. It's a vector. It's equal to the change in momentum. That's the impulse momentum theorem, right? This is our definition of momentum. This is our law of conservation of momentum in its simplest form. So you may want to review all that. And then we have the recent stuff, rotational kinematics. So I could ask, distinguish between average and instantaneous angular velocity. 3 categories of rotational, 3 groups, right? Group 1, Group 2, and Group 3. And then we have our torque, rotational inertia equations. Some we didn't cover, rotational kinetic energy, the prefixes. And the only thing that's missing from here, and I'm going to add it, is under gravity, is the equation for the force of gravity, the equation for the gravitational field, and the equation for gravitational potential energy. I'm going to add that. that UG equals GM1 M2 over R, not R squared. So all of that. So make sure that you know what all these symbols mean, and you could discuss any one of these equations in an essay question. And now here's the document that I posted yesterday with 12 questions in it. So expect to see one or more of these questions on the exam. And when you're answering them, no matter whether it says this or not, you always want to think about using words, equations, diagrams, and examples. So what determines the number of significant figures in a measurement, and what determines them in a calculation? Two different things. The calculation is determined by the rule. So in multiplication and division, the rule is the number of significant figures has to match the number of significant figures in the data you used to do the calculation, whichever one has the least number of significant figures. Right, so you should know that rule. That's in a calculation, but in a measurement, what determines it? What determines it is the instrument used and the person using the instrument. And so if you have an instrument that allows a lot of precision, a lot of digits, a lot of significant figures, you get more. Also the person using it, if you can use the instrument correctly, if you can use a ruler and read between the lines. And so the instrument and the way in which the person uses the instrument, you can give an example, like a ruler is used to measure the length of something, and does someone carefully lay the ruler edge to edge on the piece of paper, say, and read between the marks and estimate well the division between two marks in getting the extra digit? Those are the kind of things that you want to discuss. So we talked about this on the equation sheet. There's an equation for average, an equation for instantaneous velocity. And so to answer this question, you would write those two equations down and discuss it. And the idea would be you could give an example of a car, seeing a car accelerate from a traffic light, and as it passed you, how fast was it going? So you couldn't take the total distance and the total time. That would give you an average. You would have to take a short distance interval and a short time interval close to the point at which you were trying to get the instantaneous velocity. Question 4 asks you to explain the I, J, K notation for vectors. So these are I, J, and K are unit vectors. That means they have a length of 1, and I points along the x-axis, J along the y, and K along the z-axis. They're called unit vectors because they have a length of 1, and they specify a direction. Newton's 3 laws of motion. Well, the only one that has an equation, in this case, only the second law has an equation. Sum of the forces equals mass times acceleration. The first law is the law of inertia, or an object at rest remains at rest, etc. And the third law is the law of action-reaction. Remember that all forces result from interactions, and each interaction, a person pushes on a wall and the wall pushes back on the person. Those kind of examples. A free body diagram is a body is taken out of the diagram, drawn as a free body, and then all the forces acting on the body are listed. And the purpose of making one is to identify all the forces acting on a body, so that when we use Newton's second law of motion, sum of the forces equals ma, separating it into sum of the forces x and sum of the forces y, we can identify all the forces and the components of all the forces. The law of conservation of energy, let me pause the video and write that down. So if I ask question 7, this is what you should do. State the law of conservation of energy and show the two forms we used, the equation sheet and MOP. So here's the equation sheet. we use U instead of PE. So PE is the more intuitive because it's potential energy, but in physics and engineering, potential energies are often written as U. So you should know both of those notations. So if we take the equation from the equation sheet, we rewrite it this way, then we expand what kinetic energy is, kinetic energy final minus kinetic energy initial, plus potential energy final minus, and then we do the algebra, we end up with the MOP equation. And what this is saying is conservation of energy. This is a very intuitive way of thinking about it. The initial energy plus whatever we add or subtract by doing positive or negative work will be equal to the final energy. Energy is never lost or gained in an absolute sense. And the energy of a system can be changed by doing work on it, right? Friction is a negative work, it takes energy out. A person pushing a sled is a positive work, it puts energy in. These are the kind of examples you would use to explain conservation of energy. And likely there'll be some of those MOP questions on the exam. So question 8, impulse and momentum, and you'll find that on your equation sheet. Impulse is defined as the integral of F times dt, because if the force is constant, you can just multiply the force times the time interval, but if it's varying, you need to do an integral. And that impulse, that's the definition. It turns out it's equal to the change in momentum, so that's the impulse momentum theorem. So that's the difference between the definition of impulse and the impulse momentum theorem. And momentum is simply, oh, and these are vectors, yeah, don't forget. These are all vectors. And momentum is simply mass times velocity, and it's a vector, so it can have positive and negative. It can have directions. You can have momentum in the x direction and the y direction. That's the definition of momentum. And if a system is closed and there's no change in momentum, if a system is isolated and no external force acts on it, then its change in momentum of the system will be 0. And so you get that P initial equals P final, and there were a lot of mock questions on that. And for two objects, that means M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final, right? And you can give examples of that, and there were lots of examples in the MOPS of colliding cars, usually colliding objects. So question number 9 asks to talk about two equations, which aren't showing up on the printout, but you'll find them on your equation sheet, and this is the definition of torque, and it's using a vector cross product. You don't need to know, you should know what that means, but it's explained to you. It's the first vector times the second vector times the sine of the angle between them. And so this is the definition of torque. It's also what torque depends on. Torque depends on the force that's applied. You should be able to say this, right? The force that's applied, the distance from the axis, don't call it a radius, it's the distance from the axis to where the force is applied, and the angle between these two vectors. That's the definition of torque, and you give examples like the wrench example or any example you like. The second equation is that the sum of all torques equals the rotational inertia times the angular acceleration. So this is sort of like the sum of the force equals the mass times the acceleration, only in the rotational world. And so torques are added by clockwise and counterclockwise. Rotational inertia is discussed in the next question, but it's a resistance to a change in angular acceleration. And if you rewrite this equation, it actually is a way of thinking about torque, or even a way of defining torque. It's the for a given net torque, you will get so much acceleration inversely proportional to the inertia. That means more torque will give you more inertia, requires more torque, and more inertia means less angular acceleration. And so this is the definition of torque. This is a relationship between torque and motion, just like Newton's second law is the relationship between force and motion. A net force leads to a change in velocity. A net torque leads to a change in angular velocity, right? Alpha is the change in angular velocity over time. So those are all the things that you want to discuss if this question is asked. Although the equations aren't showing up in this document, question 10, I've written them down. One of the things that had occurred to me, and I might have included in the question, is the concept of rotational inertia is really best understood by a rearrangement of the previous equation. Inertia is resistance to change in angular velocity, right? Resistance to angular acceleration, and that's best expressed in this equation. An applied torque leads to an angular acceleration, and so rotational inertia is that resistance to angular acceleration. So the bigger the inertia, the smaller the acceleration, or the more torque required. Now, in order to calculate rotational inertia, it depends on the mass and the placement of the mass. So if we have an axis here and two masses here, that will be less inertia than if I move the masses out here further away, and that's captured in this equation. So this equation, anyway, talking about the equations, this equation, what you want to say is, this is the equation for calculating the rotational inertia of a point mass. And so m would be the mass, and r would be the distance from the axis to the mass. Now notice, don't call it a radius. M is the mass, and r is the distance from the axis to the mass. And if you take the mass and you multiply it by the distance to the axis, you get the rotational inertia of this mass. But if you have a series of masses, like more than one, n goes from 1 to I, which could be any number, you simply add all the inertias, all the point mass inertias together. So if we had this situation where there were four masses, 1, 2, 3, 4, we would calculate the rotational inertia of mass 1 times the distance from the axis to mass 1, and the mass of mass 2 times the distance from the axis to mass 2, and the same with 3 and 4, and we would add them all together. So this is the equation for a series of point masses. Now, not included in the question, but if we have something like a rod that isn't a point mass, what we saw in the question is we put an axis here. We simply can divide this into a bunch of many small pieces and sum up the contributions using this second equation. Or we can use calculus, which is basically doing an infinite summation. So, equation 1, the equation for calculating the rotational inertia of a point mass. Rotation 2, the equation for calculating the rotational inertia of a series of point masses. And the third equation you should know by name. It's called the parallel axis theorem. I'm not going to write that down. And it's a way of calculating the inertia for an object where the axis is not through the center of the object. And the best example for that we saw in many of the assignment problems is a rod. So if we have a rod and we have an axis through the center, we know from the equation sheet and from using calculus to derive it that the inertia of a rod about its center is 1/12 ml squared. So if we move the axis here to a position off center, the distance we move the axis is the d in the equation. And we would use the parallaxis theorem to get, so in this case, it would be the 1/12 ml squared plus the mass of the rod times that distance d squared, the distance that we move the axis from the center of mass to its current position. And that's the parallaxis theorem. So the last two questions kind of go together. The force, this is called Newton's universal law of gravitation. It's universal because it holds true throughout the universe. And it says that the gravitational force between any two objects is the universal gravitational constant times the mass of each object times the distance between their centers. Strictly speaking, this only works if they're point masses, but if the masses are round, or like in space, usually objects are so far apart that they look small and they're like points. But we know for the case of a person standing on the Earth, the distance between the person and the Earth could be 0, but it's the distance from the center of the person to the center of the Earth, which is basically the radius of the Earth. And that distance is squared. So once again, the gravitational force between any two objects in the universe is the mass of both objects times the gravitational constant divided by the distance between the two objects squared. And from that we get the inverse square law, which says that if you take, say, a satellite, the Earth's 6,400 kilometers, so say we go to 7,000 kilometers with a satellite, and we use this equation to calculate the force on the satellite, and then if we move that satellite from 7,000 meters to 14,000 kilometers, then we double the distance, and by the inverse square law, the force gets 4 times weaker. And the reason the inverse square law, the reason the force is 4 times weaker, the best way to think of it is that it's the gravitational field of the Earth that's pulling on this, and the gravitational field is 4 times weaker. And so the inverse square law is a result, really, of three-dimensional space, and here's the explanation. So any body that has mass has a gravitational field associated with it, and we often picture that field as a bunch of lines going toward the mass. So, and notice the lines as they go in become closer together, and so that's an indication that the gravitational field is getting stronger. And but a more conceptual way of thinking about this, if we think about this rather than a gravitational field, we think about this as something that's more familiar, say like a light bulb where the light is going out. So this tiny little LED light bulb is sending light out in all directions, and it's spreading out, so the light naturally, it's easy to understand, the light's getting weaker. So if we take all the light that leaves this light bulb, say 10 centimeters away, it's spread out, all that light is spread out over a hollow sphere surrounding the light. And if we go twice as far away, 20 centimeters away, that hollow sphere that the light is spread out over is 4 times more surface area, right? Because the surface area goes as the square of the radius. The surface area of a sphere is 4 pi r squared. So the outer sphere has 4 times more surface area, and so the same light is spread out over an area that's 4 times bigger. Clearly it's going to be 4 times weaker. So if you put a light meter here and measure the intensity of light and you move twice as far away, you will find that the intensity of the light is 4 times weaker. And so that's true of anything. It could be a light bulb emitting light, or a tiny microphone emitting sound, or a radioactive material emitting radiation, or in the case of the gravitational field strength, because of that spatial three-dimensional space and the geometry of space, is going to be 4 times weaker. And so the field and the force twice as far away would be 4 times weaker. 10 times far away, 10 squared, 100 times weaker. And so it's inverse, because the bigger the distance, the smaller the force, and it's inverse square, because if you double the distance, you get 2 squared, or 4 times, or 10 times the distance, 10 squared, or 100 times weaker than the original force. All right, I think we're done. Good luck on the exam.